Alloy steel. Classification of materials. Steels. Steel is an alloy of iron and carbon. A. Plain carbon steel. A plain carbon steel is an alloy of iron and carbon, and it is malleable. Carbon steels are different from cast iron as regards the percentage of carbon. Carbon steels contain from 0.05 to 1.5% carbon, whereas cast iron possesses from 1.8 to 4.3% carbon. Carbon steels can be classified as 1. Low carbon steel 2. Medium carbon steel 3. High carbon steel. 1. Mild steel/low carbon steels. Mild steel or low carbon steels and contains up to 0.3% carbon. It may classified as follows. I. Dead mild steel, C 0.05 to 0.15%. It is used for making steel wire, sheets, rivets, screws, pipe nail, and chain. It has tensile strength of 390 N/mm2 and a hardness of about 115 bhn. 2. Mild steel containing 0.15 to 0.20% carbon, has a tensile strength of 420 N/mm2 and hardness 125 bhn. It is used for making camshafts, sheets and strips for fan blades, welded tubing, forging, drag lines, etc. 3. Mild steel containing 0.20 to 0.30% carbon, has a tensile strength of 555 N/mm2 and a hardness of 140 bhn. It is used for making valves, gears, crankshafts, connecting rods, railway axles, fish plates, small forgings, etc. 2. Medium carbon steel. Medium carbon steel contain carbon from 0.30 to 0.70%. Steel that containing 0.35 to 0.45% carbon have a tensile strength of about 750 N/mm2. They are used for making 1. Connecting rods 2. Wire and rods 3. Spring clips 4. Gear shaft 5. Key stock 6. Shift and brake levers 7. Axles 8. Forging, etc. Steel that containing 0.45 to 0.55% carbon have a tensile strength of about 1000 N/mm2 and are used for making parts. Those are to be subjected to shock and heavy reversals of stress such as 1. Railway coach axles 2. Axles 3. Crankshafts 4. Crank pins on heavy machines 5. Spline shafts, etc. Steels containing 0.6 to 0.7% carbon have a tensile strength of 1230 N/mm2 and a hardness of 400 to 450 bhn. Such steels are used for making 1. Drop forgings die 2. Set screws 3. Die blocks 4. Clutch disc 5. Plate punches 6. Valve spring 7. Cushion rings 8. Thrust washer, etc. 3. High carbon steel. High carbon steels contain carbon from 0.7 to 1.5%. Steel containing 0.7 to 0.8% carbon have a tensile strength of about 1400 N/mm2 and a hardness of 450 to 500 bhn. These steels are used for making 1. Cold chisels 2. Pneumatic drill bits 3. Wheels for railway service 4. Wrenches 5. Jaws for vices 6. Wire for structural work 7. Shear blades 8. Hacksaws 9. Automatic clutch disc, etc. Steels containing 0.8 to 0.9% carbon have a tensile strength of about 60 N/mm2 and a hardness of 500 to 600 bhn. Such steels are used for making 1. Rock drills 2. Punch and dies 3. Railway rails 4. Clutch discs 5. Circular saws 6. Leaf spring 7. Machine chisels 8. Music wires etc. Steels that containing 0.90 to 1% carbon, high carbon tool steels, have a tensile strength of 580 N/mm2 and a hardness of 550 to 600 bhn. Such steels are used for making 1. Punches and dies 2. Seed disc 3. Spring, leaf and coil 4. Pins 5. Keys 6. Shear blades etc. Steel that containing 1 to 1.1% carbon are used for making 1. Railway springs 2. Mandrels 3. Machine tools 4. Taps etc. Steel that containing 1.1 to 1.2% carbon are used for making 1. Taps 2. Twist drills 3. Thread metal dies 4. Knives etc. Steel that containing 1.2 to 1.3% carbon are used for making 1. Files 2. Reamers 3. Metal cutting tools etc. Steel that containing 1.3 to 1.5% carbon are used for making 1. Wire drawing dies 2. Paper knives 3. Metal cutting saws 4. Tools for turning chilled iron etc. Alloy steels. Steel is considered to be alloy steel when the maximum of the range given for the content of alloying elements exceeds one or more of the follower limits: Mn 1.65%, C 0.6%, Cu 0.6%, in which a definite range or a definite maximum quantity of any of the following elements is specified or required within the recognized field of constructional alloy steels. Al B Cr up to 3.99% Co, Mo, Nit, W, V or any other alloying elements aided to obtain a desired alloying effect. Given below is the composition of a typical alloy steel. C 0.2 to 0.4%, C 0.3 to 0.6%, Cr 0.4 to 0.6% Fe balance. Mn 0.5 to 1%, Ni 0.4 to 0.7%, Mo 0.15 to 0.3%. Alloying elements after the properties of steel, and put into a slightly different class from carbon steel. Advantage-disadvantage of alloy steel. The important advantages and disadvantages in the choice of alloy steel from the general point of view in relation to plain carbon steel are listed in the following. Advantage: greater hardenability. Less distortion and cracking, greater stress relief at given hardness, less grain growth, higher elastic ration and endurance strength, greater high temperature strength, better machinability at high hardness, greater ductility at high strength. Disadvantage that may be encountered: cost, special handling, tendency toward austenite retention, temper brittleness in certain grades. Purpose of alloying. The purpose of alloying steels are strengthening of the ferrite, improved corrosion resistance, better hardenability, grain size control, greater strength, improved machinability, improved high or low temperature stability, improved ductility, improved toughness, better wear resistance. Effect of alloying elements. Carbon content is steel affects, hardness, tensile strength, machinability, melting point. Nickel increases toughness and resistance to impact, lessens distortion in quenching, lowers the critical temperature of steel, and widens the range of successful heat treat indent, strengthens steels. Renders high chromium iron alloy austenitic. Does not unite with carbon. Chromium, joint with carbon to form chromium carbide, thus adds to depth hardenability with improved resistance to abrasion and wear. Silicon improves oxidation resistance, strengthens low alloy steels, acts as a deoxidizes. Titanium prevents localized depletion of chromium in stainless steels during long heating. Prevent formation of austenite in high chromium steels. Reduces Martin's tick hardness and hardenability in medium chromium steels. Molybdenum promotes hardenability of steels, makes steel fine-grained. Makes steel unusually tough at variousness level. Counteracts tendency towards temper brittleness, raises tensile and creep strength at high temperatures. Enhances corrosion resistance in stainless steel, forms abrasion-resisting particles. Vanadium promotes fine grains in steel, increases hardenability, imparts strength and toughness to heat-treated steel. It is a powerful carbide former, stabilizes cementite, and improves the structure of the chill. Tungsten increases hardness and also red hardness, promotes fine grain, resists heat, promotes strength at elevated temperature. Manganese contributes markedly to strength and hardness, counteracts brittleness from sulfur. Lowers both ductility and weldability if it is presents in high percentage with high carbon content in steel. Copper increases resistance to atmospheric corrosion, acts as a strengthening agent. Boron increases hardenability or depth to which steel will harden when quenched. Aluminum acts as a deoxidizer, produced fine austenitic grain size. If present in an amount of about 1%, it helps promoting nitriding. Cobalt contributes to red hardness by hardening ferrite. Improves mechanical properties such as tensile strength, fatigue strength and hardness. Refines the graphite and perlite. Is a mild stabilizer of carbides. Improves heat resistance. Retard the transformation of austenite, and thus increase hardenability and freedom from cracking and distortion. Stainless steels. Concept. When 11.5% or more chromium is added to iron, a fine film of chromium oxide forms spontaneously on the surfaces exposed to air. The film acts as a barrier to retard further oxidation, rust or corrosion. As this steel cannot be stained easily, it is called stainless steel. All stainless steels can be grouped into three metallurgical classes. A. Austenitic, B. Ferric, C. Martensic. Based on their microstructures. Each of the classes has different welding requirements. Austenitic stainless steels. 1. They possess austenitic structure at room temperature. 2. They possesses the highest corrosion resistance of all the stainless steels. 3. They possess greatest strength and scale resistance at high temperature. 4. They retain ductility at temperatures approaching absolute zero. 5. They are non-magnetic so that they can be easily identified with a magnet. 6. They have the following composition. C 0.03 to 0.25%, C 1 to 2%, Ni 3.5 to 22% Mo, and T in some cases. Mn 2 to 10%, Cr 16 to 26% P, and S normal. They may find uses in aircraft industry, chemical processing, food processing, household items, dairy industry. Ferritic stainless steels. 1. They possess a microstructure, which is primarily ferritic. 2. Ferritic stainless steels have a low carbon to chromium ratio. This eliminates the effect of thermal transformation and prevents hardening by heat treatment. 3. These steels are magnetic and have good ductility. 4. Such steels do not work hardened to any appreciable degree. 5. Ferritic steels are more corrosion resistant than martensic steels. 6. Ferritic steels develop their maximum softness, ductility, and corrosion resistance. 7. Ferritic stainless steels have the following chemical composition. C 0.08 to 0.20%, C 1%, Mn 1 to 1.5%, Cr 11 to 27%. Martensitic stainless steels. 1. Martensitic stainless steels are identified by their martensitic microstructure in the hardened condition. 2. Because of the higher carbon, chromium ratio, martensitic stainless steels are the only types hardenable by heat treatment. 3. These steels are magnetic in all conditions and possess the best thermal conductivity of the stainless types. 4. Hardness, ductility and ability to held on edge are characteristics of martensitic steels. 5. Martensitic stainless steels can be cold worked without difficulty, especially with low carbon content, can be machined satisfactory, have good toughness, show good corrosion resistance to weather and to some chemicals, and are easily hot worked. 6. Martensitic stainless steels have the following composition: C 0.15 to 1.2%, Mn 1%, C 1%, Cr 11.5 to 18%. The structure condition known as austenite is favorable to the production of a tough and ductile weld, capable of withstanding considerable stress without fracture. Hence, for corrosion resistance and for a high degree of heat resistance, austenitic stainless steels are used in welded assemblies in preference to ferritic or martensitic stainless steels. Tool steel. Tool and die steels may be defined as special steels, which have been developed to form, cut or otherwise change the shape of material into a finished or semi-finished products. Properties of tool steels: slight change of form during hardening. Little risk of cracking during hardening. Good toughness, good wear resistance, very good machinability, a definite cooling rate, during hardening a definite hardening temperature. Resistance to softening on heating, red hardness. Red hardness, in reference to high-speed steel and other cutting tool materials, the property of being hard enough to cut metals even when heated to a dark red color. Application of tool steels: taps, drills, reamers, etc. General tool and die application: die work, tools for hot forging machine, hot trimming tools. Pneumatic tools, punches. Molybdenum steel. Molybdenum steel contains C 0.26%, Mo 0.76%. Molybdenum steel, when heat-treated, produces a structure steel, which has increased elastic limit, without correspondingly decreased ductility. Molybdenum improve hot hardness and strength of steel. Molybdenum steels are less affected by temper brittleness. It is used for making 1. Aircraft landing gear 2. Fuselage 3. Coil and leaf spring 4. Pressure vessels 5. Transmission gear, etc. Chromium steel. Chrome steel contains C 0.36%, Cr 0.57%. Chromium intensifies the effect of rapid cooling on steel. Therefore, chromium is used only in steels, which are to be heat-treated. Chromium forms carbide, and thus gives high hardness and good wear resistance. In addition, chromium increases tensile strength and corrosion resistance of low alloy steels. Percent of Cr in steel 8%, uses electrical perp 15%. Springs, ball and roller bearings. Manganese steel. Manganese low alloy steels are characterized by Mn 1.6 to 1.9%, C 0.2 to 0.35%, C 0.18 to 0.48% S, and P less than or equal to 0.040% each. Manganese increase hardness and tensile strength. A secondary effect is an increased resistance to abrasion. The steels also withstands the shock test excellently. Manganese steels are used for making power shovel buckets, grinding and crushing machinery, railway tracks, etc.